Hello everyone, welcome to another Value and Energy Data webinar. Okay, we've got quite a few people who have arrived, so it's 12:01, I think we can start. So thank you for joining us today. This is the next in our instalment of the Value and Energy Data series. So today we have an exciting session on a bunch of things, which I think I'm going to leave to the speakers to speak about. But our two speakers today are Miriam, who is the group leader for the data-centric engineering program at the Alan Turing Institute and a senior research associate at Newcastle University. I hope that's correct. Miriam secured over £1 million to investigate vehicle-to-grid technology and has collaborated with the automotive and energy industry to roll out EV charging infrastructure and investigate EV charging flexibility in mass deployment conditions. Matt joins us also from Newcastle University as a research associate in the Power Systems Engineering Group. Matt has a PhD in engineering science from the University of Oxford and holds a Clarendon Scholarship, and his research interests include distribution network analysis and whole energy systems, which is very relevant to the work we do at Catapult, but also some of our external colleagues who are joining us today. And I can already see a question. Yes, this video will be available to review afterwards. So without further ado, just a couple of things. Could you please keep yourselves on mute throughout the session, just to reduce the amount of disruption. What I will be doing is collating questions in the chat, and at the end of the session, I will be putting those questions to Miriam and David, and we will try to get as many questions in as possible, time permitting. So apologies if we don't get to your question, but perhaps we can submit them to Miriam and David for answering after the session. I guess
Matthew.
Yes. Oh, sorry, Matthew. Yeah. So without further ado, I will let you go ahead.
Lovely to be invited here. Thank you for having us. The work we're going to present to you is facilitated by several grants and projects, namely an Innovate UK grant on vehicle-to-grid technology, and the project is called E for Future. We are also funded by a Lloyd's Register Foundation grant to the Data-Centric Engineering Program at the Alan Turing Institute. The Data-Centric Engineering Program is led by Mark Girolami, and also funded by the SuperGen Energy Networks, which is led by Phil Taylor. And SuperGen brings together industry and academic partners to understand the interaction and dependencies between energy networks. During this presentation, I'll give a brief overview of the electric vehicle projects, share some key learnings from these projects, talk a bit about data collection on these projects. We will also talk about the electric vehicle network analysis tool, and then I'll give over to Matt, who's going to go into detail about the network modeling and that is underpinning this tool, and we will finish by some slides on how to secure the EV charging infrastructure with a focus on communication protocols. So to start with, we've been involved in real-world demonstrations of electric vehicle and charging infrastructure for over a decade now. The first one we started was called Switch EV, and that project really was about to check if people are willing to drive an electric vehicle. And we have come so much in the past 10 years. At the end of that project, at the end of Switch EV, one of the main findings was that people did not want to give back those electric vehicles. And the question stopped being if people are willing to use an electric vehicle. And following projects, we started to investigate what type of charging infrastructure we need and where we need to put it to meet the upcoming demand of electric vehicles. And one of those chargers is the rapid charge network. And you see the picture on the right, where we installed 74 multi-standard fast chargers installed along travel corridors in Great Britain and Ireland. And multi-standard because these chargers supported both the CHAdeMO and the CCS protocols. Then in addition to looking at what and where we should put this charging infrastructure, we also looked at the impact on the grid. And the CLNR project provided network models, network data, and smart meter data to facilitate that question, which I will talk about a bit later. Finally, right now, we're working on the E4Future project. And the E4Future project is led by Nissan with the collaboration of network operators like UK Power Networks, Northern Power Grid, National Grid, and also E.ON, who's acting as the aggregator on the project and in some instances as a supplier. This is a £10 million fund project. Around 5 million came from Innovate UK, and we're looking to investigate the flexibility that will be allowed by V2G chargers from EV fleets. We are seeing here the first installation of 20 of these chargers in Cranfield, and we're looking to install over 50 V2G chargers on that project. We have just started with the data collection. This data is coming from a V2G charger from a previous project. We are seeing here a plot that is showing the first 75 minutes of the power output of a V2G charger, which is following grid frequency. So on the top graph, we are seeing the power output of the charger, both the power requested and the power provided. And we can notice that once there is a frequency drop, so the frequency is illustrated in the below graph, we are discharging. And positive power denotes the power produced by the car and the charger. Then when the frequency rises, so there's so much, then denoted here by negative power, denoting power consumed, we see that the car is charging. We expect the E4Future project to provide similar data that shows both charging and discharging of a car battery through these new type of charging technologies. Okay. So on these projects, we collected a lot of data, over 1 million kilometers driven, over 100,000 trips, over 40,000 charging events. Those charging events were collected from different types of infrastructure, so slow chargers installed at home and at work, but also public chargers, including those 50 kilowatt fast chargers that I mentioned. We also collected data from private and fleet drivers, and we collected data from urban and rural users. And this gave us insights on how people are using these cars, but also how they are using these chargers. And in the following slides, I'm going to share a couple of insights from this data set that we collected. To start with, this data allowed us to understand what type of chargers and where should be installed. Cars are parked routinely for long periods of time at home and at work. And we find, aligned with other studies, that this is where slow chargers should be installed. These slow chargers that also would be smart to allow the control of the charging make sense at these locations where cars are routinely parked. Now, when this type of charging infrastructure is not enough to meet charging demand or is not suitable, then our charging infrastructure is complemented by rapid or fast charging stations installed either in urban filling stations or around travel routes. So simplifying it, dividing it into two groups, you have destination charging. So these are where you're anywhere going. So you're going you're going back to your home, you're going to work, and you charge there. This is destination charging. But also you have charging destination where you're going to actually charge, such as urban filling stations. One other thing I want to share from these projects is from those 50 kilowatt chargers that we installed. On the left, we see a distribution of the energy per charging event from the charging network installed in the UK, and on the right is from a charging network, from a fast charging network installed in the US. Two main points here. One is the average charging event on this fast charging network was less than half of the battery capacity. But also in the UK, a couple of years ago, we had a peak around the 7 to 8 kilowatt hour of energy transferred per charging event. And we figured out that this was because the network was being used by a newly introduced type of plug-in hybrids that had small batteries, and that type of car was not there in the US yet. Now, things are changing. So a couple of years ago, these cars had between 24 to 30 kilowatt hour batteries, and on average, the charging event was 10 kilowatt hour. So how are things changing? And will things change now when you have those bigger batteries and those bigger chargers? Just last week, the Competition and Market Authority published an EV charging market study. And one point that really stayed with me was they talked about the importance of designing charging infrastructure while ensuring that there are no areas left behind with no charging. And I wanted to share this slide from the project where we're visualizing here the energy demand per charging post. And on the x-axis here, we have when we installed the charging post. So this charging post was the first installed. And the blue here denotes that that charger was used above average. This charger here was installed last, and you'd expect that it does not have as much usage as the others. However, what was interesting to see is that here, this group of chargers that were installed towards the end of the project were used much more than previous chargers that were installed at the beginning of the project. And this raises the point that what happens if private investors just target areas where you have demand? What happens to the areas where you don't have demand? You won't have chargers installed, and that links very well to that point raised by the Competitions and Market Authority, and we need to be careful about this to ensure that no areas are left behind. One last slide I want to share about that rapid charge network, and this is showing the daily driving distance of 35 cars that were part of the trial. Now, every dot here denotes the daily distance driven. And the 150 kilometer line, that denotes the lower bound of the driving range of the cars back then. So again, those are 24 to 30 kilowatt hour batteries. We're seeing here that even back then, when cars were still, electric vehicles was still a new technology, you did not have as much charging infrastructure. Once people had access to fast chargers and had confidence in this infrastructure, they pushed those cars. We even had a driver that made a 600 kilometer journey in one day, that you can see it here. Other things that we found in the data is the energy consumption. So yes, a lot of studies rely on the National Travel Survey to estimate how long people drive a day. And what we found is aligned with the NTS. So on average, people, yes, drive 45 kilometers. On this trial, we had them drive a bit higher, 54 kilometers a day. But driving distance is not enough when we're dealing with a battery and how much energy we need. And on the right, you can see a distribution of the driving energy consumption. And so in our studies, we did not have to make an assumption of what is a 45 kilometer in kilowatt hours. We actually had a distribution of how much energy is being used by the different users. And the difference in energy used is because people drive differently. So an eco driver versus an aggressive driver would use energy differently, but also crucially, you have the impact of temperature that I will show on the next slide. For now, I wanted to share that on average, charging electric vehicle will double the household energy consumption. And this is the driving energy showing the impact of temperature. We can see that during cold days, when temperature is low, we have a higher energy per kilometer. And this is relevant when we're looking at those electric vehicles as a flexibility asset. So during cold days, they might not have as much flexibility as they would on a hot day where the state of charge is at a higher level, but also crucially, on a cold day, when those cars drive back, they will need more energy than on other days. Okay, we've also used this data to understand the impact on electricity networks. And I mentioned the CLNR project that instrumented two real-world low voltage networks. So this is where the customers are connected. One of them is an urban network and the other is a rural network. And we had data to validate this network. On CLNR, we also had smart meter data. And so what we did was we separated the smart meter data into a rural users, into an urban users. We also separated the electric vehicle data into rural users, into urban users. We had the rural network and the urban network, and then we explored the impact of different penetration levels of electric vehicles on these two different networks. We allocated EVs and smart meter profiles randomly, and we repeated this process a couple of hundreds of times to ensure diversity and to ensure probabilistic results. So what we found, so we ran those power flows to capture the impact on voltages and on asset utilization, specifically the transformers. Usually most problems happen during the peak, and in the UK, the worst case scenario is on a winter peak day. And right now we're looking at a winter peak day, the impact of voltage, even at 60% penetration of EVs, we're looking at the customer connection point, and that customer is at the end of the feeder. So that's really the worst case scenario of the worst case scenario. And in our case study, we did not find any impact on the voltage. The voltage was still within limits. Now it was a bit different when we looked at the utilization of the transformers. In the case of the urban case study, the utilization of the transformer came very close to being exceeded for the urban area at 60% EV penetration. For the rural area, the transformer was compromised at 15% EV penetration. And now that led us to a couple of important findings. First of all, this research output, which used real-world data sets and two use case studies of real networks, challenged the standard views that usually overestimated the impact of electric vehicles on the electricity networks. And to remind you, we had 60% EV penetration, no impact on voltage, and barely exceeding or close to exceeding the transformer. And in our case, that was the case because those people had access to chargers at home and at work. So they did not just rely on home charging to carry out all their charging event. But also, we did not make an assumption that those people charged at peak every day, and they didn't. And that's why we did not see as much impact at other studies that assume that people are charging an empty battery every day at peak time. The other important finding is that LV networks are not a homogeneous group. And we've seen the urban network had different behavior than a rural network. Its hosting capacity was much higher. And this illustrates the importance of bespoke studies. In our case, having access to network data from one project and electric vehicle data from another project, and it was good coincidence that two research groups were working closely, allowed us to do this kind of work, raising the importance of having access to this kind of data and this kind of network models. Now, moving on from findings from EV projects to some of the learnings and why we're using cloud technologies for data collection. I had mentioned all these 1 million kilometers driven and all these charging events that we had access to. And I have to mention here that this data was not always easy to collect and to maintain. As an example, on one of the projects, we received the data in CSV files by emails, and we received the password to open those CSV files on the phone to ensure the security. But also we received data from different partners at different times, and that was time consuming. So on this new project on E for Future, we wanted to avoid this. We wanted to automate the process, to centralize it so that we spend our resources on actual interesting things, while also ensuring secure data transfer. And we have used cloud technology. On this diagram, you're seeing two boxes. One of them is the restricted computing environment where we're collecting the data from our project partners through API, as an example, but also another box where we are collecting openly accessible data sets that I'll show a couple of examples about later on. Now, why Cloudtech? Well, first of all, it is easier to set up from scratch. It's easier to set up an environment to collect this data and to process it using cloud technologies. But also, cloud technologies provide you different options. In our case, we're using serverless computing resources. And that means that we only use those resources when we need them, instead of using them constantly, which means this will lead at the end of the month of paying less for these resources that we are using. This cloud tech that we're setting up is not really tied to a particular infrastructure, which is also an important point for us. Okay, we've collected a couple of open access data sets for us to use with, for example, with our V2G profiles to understand the impact on the network, but we wanted to make them available as part of the web tool that I'm going to talk about next. Here we are seeing PV data. This is real PV output data, 5-minute resolution that's coming from households to industrial scale installations all over the world. These are people that facilitate the sharing of this data. With a small donation, this website gives you access to 300 requests per hour, and each request is a data for one system for 1 day. The plot you are showing here is a plot from 5 systems over a 6-month period, 3 months in the winter, 3 months in the summer, in an area in London. And you can see the average PV output as a line, and the shaded area shows the lower and upper quartile. And you can see, obviously, there is a difference in PV output between winter and summer, but also during the time of the day. And this half-hourly power output data, we are using it in our simulation. We have also collected open access electric data, electric vehicle data. One of them was from WPD, the Electric Nation data. So there's around 18 months data from smart charging infrastructure, both from 3.7 kilowatt and 7 kilowatt chargers. We also collected data from Cloudtech, the adaptive charging network. They have data from over 100 chargers installed in 3 different parking garages on campus in Cloudtech. And again, we've used this data in our simulation. We've processed it into 30-minute power output data. Now, this data, while we're making these actual profiles available through the tool, we're also making available the Python code that allow us to automate and process these data sets. Okay, some of the things we want to do with this data, this open data, but also the project data, is to apply existing statistical and machine learning methods. We're not developing any new techniques. We're applying existing techniques to historical data to generate forecasts. I'm showing here something that we're excited about. This new tool called Prophet is coming out of Facebook, and we're going to try and apply it to the PV data and also to demand data to generate some forecasts. Supposedly, it works best with time series that have some seasonal effects, and right now we're trying it out. So we've talked about some findings from EV projects. We've talked about our data, why we decided to move to cloud, and now I'm going to talk about the electric vehicle network analysis tool. So this is a web tool that helps us model and simulate electricity networks. I'm wondering, how can I copy the link so people can check it if they want? Let's see. Maybe we'll send it towards the end. This link allows you to access this web page, and you can run the tool. Right now it takes around, excellent, thank you so much. I can see it has been accessed and it has been sent now in the chat. So who are we developing this tool for? We have 2 different type of users. We think having access to network models and having access to modeling those networks is a skill that is not widely available outside a certain academic community, outside the DNO and some of the consultants. But we think to achieve digitization, to understand really the benefits of flexibility from low carbon technologies such as EVs, we need to have some tools available to flexibility providers to test these, to test their control algorithms, so that they can, in discussions with the DNOs, they can have a tool to say, we've tried this, this is the benefits, this is the impact, this is how we can help. While those flexibility providers might have the data and might have the capabilities to forecast things and to optimize, they might not necessarily have the tools to model the impact on the network, but also they might not be interested in having people in-house to have these capabilities. So we think this tool can help with this. Another user type we think is the actual DNOs themselves. There's not a lot of LV visibility right now, so we don't know what's happening with loads. We don't know what is the grid capacity at LV, and it's really important to understand what's happening so we understand the impact of those low carbon technologies. Right now, there's not enough models yet at this stage. Yes, if we read the digitalization strategies that have been just recently published as part of the Rio ED2, yes, DNOs want to get there, but until then, there's a gap, and we think what we're doing is one way to fill this gap. So we need a lot of LV network models, we need a lot of test cases, and we are providing one. So So the tool, the link you access, this is the proof of concept to check the infrastructure, to check the front and the back end happening in the cloud. We want to get to this front end you're seeing in front of you, where a user can change the network ID. So you can check an urban or a rural ID. You can also change some network parameters, such as the transformer size, but also you can use some of the data we're making available, such as, for example, this PV data. Crucially, we think one of the main thing of this tool is it allows users to upload their own data sets so that they can test their own data sets, the impact on the network. Now, it is important to mention that once you upload this data is not kept. This data is disregarded as soon as the simulation is finished. So you choose your parameters, you upload the network, and then we are running an integrated LV-NV network to give us a different views of this network. Matt in a bit is going to give a bit more detail about the network, and we are running power flow analysis using OpenDSS. OpenDSS is an open source tool that carries out what I mentioned, power flow analysis. Now, power flow analysis allows us to answer an essential question. It allows us to understand what's happening with the network by determining quantities, mainly voltage at various locations, and also currents to know if we are exceeding network equipment such as transformers. And power flow analysis, what we're running in this tool, allow us to answer questions such as what if. Now, if we're just monitoring and collecting data from the network, we know the what now, but we want to know the what if. What if 60% of houses on this network have electric vehicles? What if 100% have electric vehicles and PVs? Is our network future-proof to hold this much new LCTs, or are we going to go through some problems, and what can we do with these problems? So this type of questions we're letting people answer through this tool. Now, before I give over to Matt to go into detail about the use cases that we can use in this tool, some of the outputs, I wanted to briefly just talk about the infrastructure. So here we're seeing a front end. So this is the web page that you accessed, and then you have a back end where the actual simulation is happening. A user can configure the simulation in the web browser, but that simulation is run in the cloud. And to allow this information flow between the front end and the back end, you need something called an API, an application programming interface. So now just to give a comparison, the I in GUI, the I in graphical user interface, is the interface for the user with the machine. Now the I in the API is the interface between the two machines. And so we are using something called a fast API, which is a web framework that allows us to define and build that API. We're using Vue for the front end, and we're using Azure Functions and Azure Storage for the back end. Now, how to access this tool? In the website link that you've seen, but also through a GitHub repo where you can download everything, including the configuration files that will allow you to automate the deployment of this tool on Azure, for example, or another Cloudtech provider. Now, without further ado, I'll give over to Matt so that Matt can talk in detail about the MV-LV network model that is running in the backend. Matt, over to you.
Okay, thanks very much, Miriam. And again, thanks to to Steve and Energy Systems Catapult for inviting us along to speak. So yeah, I'll talk about, in terms of the event tool, this MV-LV network model that we've implemented within the tool. And also I'll talk a little bit about some of the some analysis techniques which we've been developing for considering how low carbon technologies could impact on networks, so that because these networks are quite big, it's important to be able to analyze them efficiently so that you don't have to wait half an hour to run these sorts of models. And this is work that I've been doing with Miriam, but also with other colleagues at Newcastle, David and Sarah, Phil Taylor at Bristol, Pete Armstrong at the startup Mixergy, and then also Pam at Turing. And I'll talk for about 15 minutes, firstly about some of the network modeling work that we've done that has actually built those MV-LV networks. And then in terms of the analysis, I'll firstly talk about the actual implementation within the event tool. We're using this particular technique, load aggregation. And then, although it's not going to be implemented in the event tool itself, I'll also, just because it's on this sort of topic of impacts of smart devices on distribution networks, I'll also talk a little bit about some matrix factorization techniques that we developed for studying frequency containment in the context of these networks. There's a little bit of background. In the past sort of 20 years, there's been a sort of explosion in distribution network modeling. So back from the early days, there's some within the UK, there's this sort of PB power network, which is the ones that Miriam was talking about a little earlier, going through the UK generic distribution system, and then Electricity Northwest LV networks. On the US side of things, there's a lot more big networks. So a little over a decade ago, there was the IEEE test network. Of all of these, well, sorry, just to highlight one of the really interesting ones is that NREL and Comillas in Spain, University of Comillas, have been developing some synthetic networks in the US. So, for example, they've got this model in San Francisco, which is sort of over 1 million nodes and is modeling the whole Bay Area. So it's a sort of, there's this explosion of people looking at these networks to think about how do you develop scalable solutions that will work not just on one network, but when you apply it to the whole huge areas. So in the European context, we're missing a medium voltage MV-LV network. And compared to American networks, you have much more extensive low voltage systems. So all of these blue dots for this EPRI K1 feed that we have here might have between 1 and 20 customers, say, whereas it's very common. You might have 100, 200, 500 customers for a single substation in a European style network. So we wanted to develop a network that would have that LV network diversity that Miriam mentioned, but also include the coupling at MV, or in UK parlance at HV. So this is sort of international versus UK parlance. And is also suitable for these sort of scalability questions. So instead of building a network from scratch and having to validate it all completely from every single use case, we instead decided to work with 2 of those network models that I just mentioned. So for the MV networks, we're using the UK generic distribution system, which has been, as I say, existing for around 15 years. And then on the LV side, using the low voltage network systems solutions. And just to give you an idea what sort of area this is representing, this is from Northern Power Grid's map. You can perhaps work out these sort of different areas. This is from this ODI, Open Data Institute at Leeds have developed this tool that you can look at the area that different primary substations are meeting. And in rural areas, you can see it's pretty big. When you sort of go into the center of town, it sort of starts getting quite small. So you get quite a big range of behaviors. So of those UK generic distribution systems on the MV, we use the underground and this sort of mixed feeder, which has a mixture of underground and overhead networks. And as I say, we allocate to each of these loads a low voltage network that is of a similar power. There's some randomization in there to make sure we get a good spread of network types. And there's 25 of these networks within LVNS. And we allocate these, and then we can run these power flows. And to make this as useful as possible for people, there were 2 sort of steps we did in development. So firstly, we reduced the number of nodes by splicing branches. So if you look at this, you can see that we have these very nice curves, which are built by sticking together lots of straight lines. And then if you do enough of them, you get these nice curves. But it means that from a power flow point of view, you have a lot more nodes than you need. So it turns out you can stick those together without affecting the power flow solution. And we did this for all of the LV networks before they were allocated. And it turns out this is numerically exact. And you can see that you get between 5 and 18 times fewer nodes when you do this splicing. Secondly, although the networks in themselves have been they've been used for many years, and so there's a lot of trust, we wanted to make sure that the solutions that were coming out weren't completely ridiculous, basically. So we checked the MV voltages are looking pretty reasonable there within these dashed lines of the bounds, and similarly for the low voltages as well. So these here are plotting the quartiles. And then in terms of powers, again, because we're not allocating exactly the same powers to each of those MV loads, you get a slight difference when you go from the UK GDS to the MV-LV power flow at the primary substation, but it's pretty small in terms of the rating of those particular substations. In terms of the sort of final bit that we did was we also took voltage measurements from, or Mixergy provided us. Mixergy is a company that makes smart hot water tanks, and they measure voltages. And we took the peak voltage data for the peak from 5 till 8 p.m. in January 2020 for 100 loads. I've plotted the distribution of 30 of these here. And then using that data, plotted a quantile plot of the solution of our model at peak against the tank voltages. And we want this to lie along the line y equals x. We're doing reasonably well. We're a bit off on the lower end, and that's not too surprising though, because the tank is measuring at the actual tank itself, so you have the voltage drop within the house, whereas our model is only modeling to the point of common coupling, at your switchboards. So that's on the model side. So we've built these relatively large scale models. They're 100,000 nodes apiece, something like 20,000 customers, which is on the high end, but these models at the moment are only modeling residential customers as is. So that's why we're on the higher number of loads. You might be more commonly getting between 5 and 10,000, but not you would get this on. These aren't completely unreasonable. You get this LV network diversity that we were talking about in terms of the spread. So I've plotted here each of the 75 LV circuits range and median voltages for the underground circuit here. And then you also get this MV level coupling as well. So for that mixed circuit that I showed you, you can kind of see these are the three. These are ordered by where they are in the network. So you kind of get to see this nice structure in the MV voltages that are coming through there. So the challenge with these, as I say, they're relatively large scale. You can run these models in OpenDSS, and it might take 5 seconds, 10 seconds, depending on how fast your computer is. The challenge is if you want to do these load flows over and over again. So the two analysis techniques, the first one, which is implemented the event tool, is load aggregation. So what we want to do here is we want to take a whole load of profiles that we're getting from different places. So Miriam mentioned the WPD Electric Nation, this Cloudtech ACN, and then also we're interested in heat pumps, for example. So this is from some data from some of the folks over at UCL. And what we've got is, so here I've plotted 10 individual profiles, but these all have, I think this has got about 100, and these have about 1,000 profiles a piece that we're looking at. And plotted here, I've got the quartile, so this is the range up to here, the 75% percentile, and the median happens to be 0 for all of because as it happens, more than 50% of the EVs in this particular set are not charging at any one time. And we want to see what happens when we run these through the model, and this means that you have to do 48 power flow solutions, so that's actually relatively slow. What we do here is, instead of modeling every single one of these LV networks in detail, we instead pick a couple that we might be interested in. So let's say we're interested in one at the end of the feeder and one quite close to the substation. We model those in detail, and then for all of the other loads, which residential, we just we take what the demand is and we sum it together, and then we call that the demand of those particular points. You get slightly different answers because there are losses in these networks, so there are techniques to account for that. There's also unbalance as well, which again you can to an extent account for. There will be slight differences, but it's relatively minor. So this is a nice way to think. It's less useful if you want to model a sort of try and get a super scalable solution, but it means that if you want to capture that LV diversity and the MV coupling, then it sort of ticks both of those boxes. So here again for these two circuits, I've got the quartiles here, and when you add, here I've put in 33% of locations having electric vehicles and heat pumps based on those profiles I just showed you. You can see that the spread of voltages changes for those two networks. With this 1101 network, turns out you end up with some under voltages here. So this is kind of preliminary work. We're still developing this. Come September, this should all be finished. Yeah, there's sort of interesting. The sort of interesting questions where this is going is that you can, instead of having these unconstrained profiles that I've showed you here, you can instead have a smart, flexible system, as Base has been telling us in the past week or two, where it's very cheap in the middle of the day. And instead of these profiles looking like this, you can imagine that the medium profile could come along and sit really high in the middle of the day, and then come on as everyone tries to charge during those times. I'll finally go through this second point where we're looking at the sort of most extreme coupling. So when you have frequency containment, as the frequency drops, you get to a point where some devices are paid by National Grid to come on without any delay when the frequency reaches a particular point. So the question that we want to ask is what happens to distribution networks, because the frequency is common across the entire country, give or take. And so all of these devices, everyone on the same street, all of their devices, if they're providing this reserve, whether an electric vehicle or a heat pump or whatever it might be, could come on, and we want to know, does this cause problems in the network? So if you want to run this with every single network that you have, then one particular way that you can speed up analysis is to use a linear model. The challenge here is that as you get to these points when you have 100,000 nodes, you start using tons and tons of memory if you have a model that looks like this. So for example, if you have 50,000 nodes, you'll be looking at 40 gigabytes of memory, which is beyond what the normal laptop would have, for example. So to get over that problem, we use two tricks. So firstly, we use sparse multiplication, which is the idea that if you have a matrix which is mostly zeros, you don't have to store and multiply those. So that's sort of very efficient. And secondly, if you have matrices which are low rank, which means they're sort of simple in a specific sense, then you can take that big matrix, split it into smaller matrices, and it turns out that this is much faster. So instead of doing, let's say, 1,000 squared operations, you're instead only doing 2,000 operations, so 1,000,000 versus 2,000. So you end up needing much less memory and much lower, much less memory and much faster computations as well. And in terms of the results, we ended up with the method that we described in the paper, something up to 30 times less memory and up to this is about 24 times faster, sorry. And similarly, in terms of how much less memory you need, it's all running at less than 10 seconds. So you can just run this on a normal laptop, just press play and it will give you the answer pretty quickly. And in terms of the actual impact on the network, it turns out that 3 kilowatt devices, which might be a hot water tank, you can put a lot more of that on than you can a 7 kilowatt fast charger. So if you're doing this frequency response with bigger devices, it's much more problematic than with smaller devices. And similarly, if you put a lot of the devices in individual LV networks, if it's a whole load of new builds, for example, or a very wealthy neighborhood, then you get problems a lot more quickly than if they're dispersed around the network. So that's about it for me in terms of conclusion. So this increased coupling will mean that we'll need new higher fidelity models and analysis techniques to look at those models. These two methods that I've presented mean that they're very practical. You can run them in a few seconds on your laptop. You're not having to go and make a cup of tea while it runs. And the event tool, as Miriam mentioned, will mean that you can look at impacts of not just the unconstrained charging as I've presented here, but also vehicle to grid as it interacts with the things on the transmission network when it's very windy. Going forward, I think from a data point of view, it'd be very interesting to look at in terms of the next generation of MV-LV networks, take that sort of relatively simple quantile plot and do it much more comprehensively, looking at the whole spectrum of times and making sure that the coupling is all making sense. And then in terms of fixing issues when they occur, things like soft meshing using power converters haven't really been looked at in this context. So thanks for the invitation there. That's everything from me. Those particular models, you can go onto GitHub and you can download those from on there. And with that, I'll pass back to Miriam.
Jack, I wondered, so the next part is going to be on communication protocols for electric vehicles, but also a bit about how we secure the EV charging infrastructure. And I wondered if you wanted to take some questions on what we have talked about already, about the tool, about the network models, while I try to find my slides back up again.
Yeah, no problem. Okay. So one of the themes that's been coming out in the chat is around the opening up the data and information as part of the tool. I think you mentioned a couple of times it was going to be open access. And some people were asking about access to the data that underpins the model as well. Is there an intention or to open up access to that data that you've produced, or put a license on it that will mean that people can use it?
Sure. So there are three different components of the tool. There is the Cloudtech that is allowing us to deploy this website that allow user to change parameters and then send a request to the backend to simulate a network model. So there's that. And these are, we'll make them available in a configuration file if someone is interested to run this themselves. And the point here, if they wanted to change the network we're using, or if they wanted to add a new component, such as a cost component, so there's that. There's the network modeling aspect, and these are already available on GitHub, as Matt mentioned. And then finally, there's the data aspect. Some of those data are already available openly through their provider. What we are planning to provide is some smart meter and electric vehicle charging data. That's also going to be probably provided under the Creative Commons Attribution Share Alike. So if you use this data, just attribute it to this project.
Fantastic, thank you. A question from Tony Shorthouse. What's the impact of clustering charge points through a single LV substation, and also the impact of combined heat pumps and charge points? I think, Matt, you touched on this a little bit, didn't you, as well? Or you've both touched on elements of this.
Yes.
Matt, you want to take the heat pump part, and I would wrap up a bit with the CLNR networks.
Yeah, so I think I think that it depends. Yeah, so if you're literally doing as I did in that if there's no problems on the LV network, you don't actually need to model it except for the sort of losses and the unbalances I mentioned. So there's no reason that you can't cluster. I guess clustering is kind of similar to this aggregation that I was mentioning there. So it should be that, and if it's in terms of the aggregation in terms of lots of devices on MV, you also get it more smoothly. You have this sort of diversity as well. So yes, I don't think there's any particular challenges around doing that. I don't know if that answers the question. And in terms of rural networks, I think that again, power flows are power flows are power flows. At the end of the day, you have different cables. You have cables and you have overhead lines which have slightly different characteristics. And obviously, rural networks are much longer than urban ones, so you tend to have more voltage problems. So I don't know that there's a particular challenge there other than you get more voltage issues rather than power flow issues compared to urban networks.
And to follow on that, the slide I'm showing right now, this is exactly what we have done. We investigated the impact of clustering charge points through a single LV substation. One of them is a rural LV substation, and the other is an urban one. And we tried to understand what happens if we had 0% penetration, 60% penetration. So with 60% penetration, this considers a clustering where 60% of these households have one electric vehicle. And as we mentioned, the rural network showed problems much before the urban network. 15% clustering of EVs on that LV substation caused problems, while with the urban case study, 60% EV clustering on that network barely started showing issues.
Fantastic. I hope that answers the question. I'm going to paraphrase a statement from David Phillips as well. Is there an implication for when we're looking at local area energy planning and smaller scale networks that manage themselves essentially away from some of the mechanisms of the grid? Is there any implication or ramification from this research on the merit order of who gets to charge at what time and what priority should be given to different devices?
This research and this tool is actually providing a tool to answer these questions. So for the specific local area that we could be talking about, we need to have a representative or a digital representation of that network so that we can understand what's happening now, what is the baseline of this network, and then when we start charging, what happens. And then in the case of problems, then what do you do? Do you make sure no one is charging at full capacity, or how do you decide these things? And the output of that control algorithms that allow to change the charging rate could answer such question. Matt did a case study on peer-to-peer. Maybe this is relevant to this question, Matt?
Yeah, it was in the PowerTech paper which I referenced. There was, we looked at a case which is similar to what Miriam mentioned, where you say that some people on one LV network want to trade with another LV network, but if they were to do so, then they'd cause a voltage constraint. I mean, I think that maybe going forward, where this is leading is a sort of complement to the reliability indices, which would be the flexibility indices, which is how often do distribution network operators stop their customers providing those flexibility services because of where they happen to be on a network, because that is something that network operators can and perhaps should be incentivized to address, but they can't do it all the time in the same way that they can't do it all the time by with the reliability stuff. So I don't know that we have a particular viewpoint on it, but I think, as Miriam said, it's a very interesting sort of policy question going forward. What is the best way to address those issues?
Thank you for that. And the final question before you move on, have power quality implications or harmonics been considered for high penetration of EVs or heat pumps? And does the model allow for harmonic profile input?
Nice. No, so OpenDSS allows you to look for that. We are not looking for that specifically. And just a side note, there are a couple of projects happening right now in Europe that shows the impact of electric vehicle charging on supraharmonics, so not just harmonics. And the problems there is how do you monitor the network. So monitoring equipment is not so widely available, is not so cheap to understand the impact on supraharmonics, which is happening right now. And I'll mention at the end of the slides a smart charging webinar that we organize. The latest episode is specifically on supraharmonics. Matt, do you want to add something on that?
Yeah, so we will be modeling unbalance in this particular project, so that will come out. That'll be one of the outputs. In terms of harmonics, we hadn't been planning at this stage to include that. I think, as Miriam said, it's a super interesting space at the moment, and I think OpenDSS, as it happens, was built in the first instance as a harmonic solver, so it's got a lot of capabilities in that area. So maybe that's sort of a future work thing for the project going forward.
Fantastic. I think that covers most of the. Sorry, Miriam, go on.
No, I was going to say someone is going through the slides, so if they want to have a question on a specific slide, then let us know. Otherwise, I'm going to take back control.
Sure, please do.
Yeah. Okay, here we go. All right, so Jack, do I understand there's no more questions, and should I move on to the last bit of the presentation?
Yes, please.
Okay, so in the first part of the presentation, we kind of made a bold claim saying that network modeling capability is not widely available outside the network operators and the consultants. And our contribution is to make available a test case MV-LV network, but also a tool to allow people to model and simulate a network to understand the impact of LCT technologies. Happy to hear feedback on our claim, and if there's actually a gap we're filling. Now, that was the first part. The second part is something that Steve asked us to talk about when he invited us to this, is about what are the challenges that come from making energy data open, in particular challenges of deploying these solutions in the real world. And two main things I want to talk about here is communication protocols, which is a common language that all these low carbon technologies would talk so that they would allow coordination, but also the security of these communication. So we recently published, what's happening with the slides? Can I confirm what you're seeing from my slides?
So I can see slide 30 at the moment, Miriam.
30.
Yeah.
Okay. Here we go.
Now 31.
Okay, excellent. Okay. So in this white paper, we reviewed the threats around the electric vehicle charging infrastructure, but we also provided examples of best practice and recommendations on how to secure it. In the white paper, we talked about securing the hardware, the software, and the communication. In the upcoming slides, I will only focus on the communication of the data. Now, in the white paper, we also have a section about PKI, a public key infrastructure, which is used to authenticate entities and encrypt the communication between these entities, but I won't go into detail about the PKI here. A bit of context, there has been attacks on automotive and power systems. We heard about the Ukrainian blackout, but also there has been some items talking about hacking a charging station, and also those white hackers that wanted to help, they provided what went wrong and how to make it right. And this information is available online for entities who are developing charging infrastructure and want to make these charging infrastructure are secure, because we want to avoid in the very near future where we have millions of these devices that are not secure. Either we have a serious threat or we are going to have stranded assets and the infrastructure that should not be used, and we have to replace it. Okay, so this is showing the possible attack vectors in the EV ecosystem. So we're showing the different entities involved, from the electric vehicles and the charging station, but also to the operators who can control these charging stations. And the red arrows are the attack vectors, but we're also showing data exchange and electricity, where these are also can be considered attack vectors. To have a framework on these attacks, we usually divide them into confidentiality, integrity, and availability attack. attacks. So confidentiality attack is when a party that was not supposed to know about this information got access. Integrity is if some sort of information was modified, and availability if the infrastructure is not available. And these type of attacks have impacts on social, physical, but also cyber. And this table that you can find in the white paper is a way summarizing different type of attacks, such as, for example, denial of service. So you don't have any more access to that charger. Or an example of an integrity attack is that the charger is sending a wrong state of charge information. And now talking about the information exchange between EV ecosystem entities. So talking here about the communication protocols. So we need a common language to share data across organizations, across entities in the EV ecosystem. And the main problem right now is that entities are using their own protocols. They're using proprietary protocols, talking their own language. And we need to use open and protocols and standards, but also we need to converge to very few languages. Because imagine if on one street you have, let's say, 60 households with 60 chargers, and these 60 chargers are talking 4 to 5 languages, so 4 to 5 different communication protocols. How are you going to coordinate those chargers? How are you going to make sure that you aggregate those chargers to provide one service to help the DNO? So communication protocols is key. And we also need to ensure that those communication protocols are secure. So this slide is showing So to mention here, so again, communication protocols provide a set of rules and guidelines to facilitate the communication and data exchange between two or more entities. On the slide, we are showing different entities involved in the EV ecosystem. For example, this is the electric vehicle, this is the electric vehicle charging equipment, and usually we call that front-end communication. Examples of front-end communication is the CHAdeMO protocol and the ISO 15118 protocol. And then you have back-end communication between the electric vehicle charging unit and the third-party operator. Whether that is an energy supplier like we see in the UK, for example, Octopus or OVO, or whether it's the actual charge point operator. Examples of open communication protocols are OCPP, OpenADR, also EEBus. One of the advantages of EEBus is that it allows communication to EV charging infrastructure, but also to other low carbon technology equipment, such as, for example, heat pumps. Okay, so I wanted to focus here on this link. So going back here, this link, the front-end communication between the electric vehicle and the charging supply equipment, which is highlighted here again. In the white paper, we looked at CHAdeMO, we looked at ISO 15118, and the CHAdeMO protocol does not have enough security measures in place. The CHAdeMO Association are aware of that. They might be working towards some sort of security. We also assessed ISO 15118, and it does have security measures in place. Now, looking at the back-end protocols, we also looked at OCPP and the rest, and these protocols have security measures in place. Finally, to mention that we were part of the steering group of PAS 1878. Our role in that steering group was actually on the communication protocols and standards and not specifically on security. But as part of the white paper, we have went through the security measures there's in place. And one thing is worth mentioning that in the past, they propose an architecture that exchanged messages using a PKI infrastructure. So so there is information in place for companies that want to start now and want to ensure that what they're deploying is secure. Finally, a lot of things I mentioned, we talk about them in a smart charging webinar series that we organize. The latest one is on superharmonics, but we have many on cybersecurity, focusing on communication protocols, but also on PKI infrastructure. All of this work is possible, of course, through the funders, but also through my collaborators. And we have a project website where you can check about their profiles, but also some of the other things they work on. And for more information on our work, these are the links, including the network models that Matt mentioned and the GitHub repo that's going to be made available soon that will include the infrastructure about the web tool, but also the Python code underpinning this web tool. So with that, I'd like to thank you for your attention and looking forward to your questions. Thank you.
Thank you very much. Fantastic. So I think we have one further question from Tony Shorthouse. Should home and workplace charge points utilize the same comms protocol as public charge points?
Usually you have, so let's look at the, and maybe you're alluding to the OCPP. Anyway, if that's the case, so you'd need OCPP to provide you some sort of transactional information. So it'll provide you how much energy was used, for example, if you want to remunerate someone who is using their fleet car and charge it at home. So OCPP gives you this. And also OCPP gives you ways to deal with the charger. So check that it's working properly, that other communication protocols that are really linked to the energy system, so that the DSR does not provide you. So in an ideal world, I would think a charge point at home or at workplace would include something like, for example, EE-bus to allow that charger to participate in DSR services, but also it includes OCPP to allow you to do this transactional data and to also troubleshoot the charger if you need to, that protocols such as EE-bus does not give you.
Fantastic, thank you. Hope that answers your question. And are you capturing wireless charging with wireless data transfer?
We're not looking at that. I think ISO 15118, so the communication protocol between the electric vehicle and the charging station, so where this matters, allow a use case for wireless charging in their upcoming version. I think ISO 15118-20 edition 2 will have a use case on wireless charging.
Fantastic, thank you very much. Owen asks, have you considered interfacing with vehicles rather than the charge point?
I mean, if you look at, let's say, Tesla, for example, they do interface directly through the vehicle. Now, the question is, if you interface directly through the vehicle instead of the charging point, so the charging point, you know where it is installed. It is on this particular network spot. It is not moving. So through the charging point, you know what's happening on the network. You can help that part of the network. If you're interfacing directly through the vehicle, you'd lose that because you don't know where the vehicle is. So this is a valid use case. We are doing it right now. In the future, so in the EV infrastructure in the future, how should we do this? How should we control the charging of the vehicle? Is it directly through the vehicle or through the charge point? I would advocate through the charge point because you have that link to the physical infrastructure always in that place.
A good answer. Right, we're coming up to the end of the webinar now, so I think we will wrap up and say a massive, massive thank you to Miriam and Matthew for what was a fantastic presentation. What I will do is for all of the guests today, we've got some applause coming through as well. What we're going to do is post the video to this webinar on our YouTube channel, for which the link will be circulated along with all of the links that you've posted today. Other than that, thank you very much to all of our colleagues, internal and external, that have joined us today. Thank you again to Miriam and Matthew for a scintillating webinar. And next time we have Ayrton Bourne from UCL. So please join us again in a couple of weeks' time.
Great.
Thank you very much.
Jack and Tabitha, for having us.
Thanks very much.
Thank you. Bye-bye.